So here we have the IGCSE 0620 Chemistry Paper 6. That's the alternative to practical. It's a 1 hour paper, as you can see. This is the specimen from 2023. You know the drill, you have all the instructions. Right, it's a 40-mark paper and there are 12 pages. So just to check, if we go to the very end, right, that's page number 12. So we have all of them. Right, it's not just going to the end and checking whether the last page has the number 12 on it. You just flip through the pages when obviously they ask you to open the paper during the exam. Don't turn over the paper before that. So just check whether all the pages are printed and there's anything blank that should say blank page, right? Hopefully there's no misprint. It could happen. It would be very, very rare and unusual, but there's always the possibility because right, mistakes happen. Okay. So here's question 1. Right, so because there's an alternative practical, all the questions you would come across over here are ones that have the practical aspect to them, right? So you're probably not going to be asked about the extraction of aluminum because that's not something you're going to be doing in the lab, right? You're not going to be asked about radioisotopes. Most likely, there was an experiment about radioisotopes. I think that was physics. So yeah, right. So you're only going to be asked questions with regard to things that you can do in the lab. Right. So all the practicals that were there in the syllabus. Now here it is. A student investigates the rate of reaction between magnesium ribbon and excess dilute hydrochloric acid. Right. So what you can do when you're answering this, you're like, okay, fine. They're putting acid, a metal, and acid. Right. So what are you going to get out of that?
Uh,
Right. You have metal plus acid. And what does that give you?
wait, hydrochloric acid for this situation we are in.
Alright, so you've got magnesium plus hydrochloric acid will give you what?
To give hydrochloric acid or no?
You already have hydrochloric acid. What about the products?
Yeah. So, mm,
You're going to get a salt and what?
water.
How are you going to get water out of this? There's no oxygen in the whole thing.
Wait,
What's the general equation?
wait. Will there be a gas?
Yes?
Hydrogen gas?
Yes.
So it will be. Um. Okay. Wait.
What's the salt you're going to get out of this?
Magnesium chloride, and the gas would be hydrogen gas. Yeah.
Alright, so this guy's gas, this guy's always write the state symbols. This guy's aqueous and this guy is solid.
Is it
Okay.
important to write the state symbols as well?
It is important to put in the state symbols when you're writing down equations, right? And I don't know whether they've asked you for the equation later on, right? It doesn't seem to be, but for your own good, right? Write it down, right? So you know what's happening. It will help your memory, it will help your understanding. So, first of all, they're asking about apparatus, right? What is apparatus X and Y?
X is conical flask
X is the conical flask.
and Y is tube.
No.
Measuring cylinder.
Huh?
Measuring cylinder.
Measuring cylinder.
Or a gas ring.
Gas what?
A gas ring.
I'm sorry, I can't make that out. Gas what?
A gas ring, like.
Gas
A,
syringe? No, 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 no. We don't have a gas syringe here.
okay, that must be wrong.
Alright, the gas made in the reaction is hydrogen. Describe how the student can test that the gas is hydrogen. Give the expected result.
Mm, The test would be a burning splint at the end of the test tube containing the gas.
Right? You can use burning or lighted
Yeah,
splint, and the result would be
a squeaky pop.
people.
Yeah.
Right? Squeaky pop.
Yeah.
We just learned popping sound.
Yeah.
Okay, so here's a graph. The result, sorry, the figure shows the results for each experiment. So you got time and volume of gas. So you can see in experiment 1, you had much more gas being produced over a time of 120 seconds, that's 2 minutes. Whereas in experiment 2, you have half. So it's going up till 80 centimeter cube. Right? In experiment 1, it's only going up till 40 centimeter cube in experiment 2. And are they plateauing around the same point? I believe so. It's just about the same that they're plateauing. Right? So if they ask you to, right, I haven't seen the question. If they ask you to describe the result, right, that means that you're going to talk about what the graph looks like, right, or if it's a table, not necessarily a graph. In this case, it's a graph, right? Talk about the trends, values, right, and etc. details. Right, so what the results look like? Are they increasing? Are they decreasing? What's the maximum value? Right, the comparison between them, etc. If they ask you to explain the result, then that means you're going to talk about the science behind it. Why is the result like this? Okay.
Yes.
So use the figure to determine the total volume of gas made in each experiment. I believe that's pretty obvious.
It's 80.
So in experiment 1, it's 80 centimeter cube, and in experiment 2, it's
40.
40. Right, they've already given cm cube over here, so you just need to put in the values. Okay, use your answer in C1 to suggest what the student changed in experiment 2. Suggest, right? So what does suggest means? Suggests means giving an educated guess.
Or an advice.
No, not an advice in this case. The student did change something. You're trying to guess what they changed to get this result.
Could you scroll up to the diagram?
Substantially.
They changed the volume of the gas.
How can
Decrease.
the gas is the product? So how can they change the volume of the gas?
The student decrease the temperature.
Will the temperature decrease the volume of gas, or will the temperature decrease the rate at which the volume of gas is changed?
Yeah.
Right, so obviously there's a difference between the rate and the volume itself.
Could you zoom out a little so I can see the question and the diagram at the same time?
Yeah.
Yeah.
So take a look at this part as well. This is what's happening. Right? Investigates the rate of reaction between magnesium ribbon and excess dilute hydro. Okay, fine. So for the answer for that is over here, right? So it's not isolated. If you're stuck, you go back and look at the previous part, see if you can get a hint, and right, you get not only a hint, but you get the answer as well. It's to investigate the rate of reaction, right? So the rate is how much gas is being produced over a certain period of time, and so the rate of reaction is actually, I mean, it's not so much the rate, I guess, right? The rate, right? You're getting more rate means that it's happening quicker. So you're measuring it to the volume of gas is more. So this is not so much the rate. It is in the sense that you're getting more gas per unit time, right? It's not happening more quickly, right? It's not happening more quickly. It's just you're getting more in that same amount of time. Now, point is, what do you have? You have magnesium ribbon and excess dilute hydrochloric acid. So the hydrochloric acid was already in excess, so it was more than you needed, right? So what does that mean? Can you explain that to me, right? What does that mean? When I'm
Is that
perform at the end of the reaction, what will be left unused?
hydrochloric acid?
Sobi, are you following?
Yeah.
Right, the hydrochloric acid is in excess, means when the
Oh, that's what that I think that will be left over.
so the hydrochloric acid will be left over. All the magnesium ribbon that's added to this will be reacted,
Hmm.
which means the volume of hydrogen produced is dependent on what? The acid or the magnesium?
The magnesium.
Acid.
The magnesium. So if you are having a change in the volume of gas produced, what does that mean?
We have added more magnesium.
We've changed the mass or we're using less magnesium.
Like how the amount of the limiting reactant.
The limiting react, yeah. So you could use limiting reactant, but over here, because you know the limiting reactant is the magnesium ribbon, right?
Yeah.
And so you can say the student,
Can it also be the suggestion can also be like this like use the lower concentration of acid
uh, mm,
or use
they
the lower temperature.
look again. The temperature will only cause the reaction to carry on for longer,
Hmm.
right? And you can see that in both they're plateauing at the same time, right? And they've been timed for 120 seconds. So
I think it doesn't change the final volume unless the reaction is reversible
what
for
what,
the
what does reversibility have to do over here?
no like if it was like reversible if the reaction was reversible then I think the this the lower temperature would slower the rate, wouldn't it?
Again, right? The slowing the rate means the reaction will take longer to go, longer. Over here, the reaction is not taking longer. It's happening in the same amount of time. What you're getting is a different
Yeah.
volume of product, right?
Like,
The volume of product that you're getting is changing. That means that you are changing the amount of reactant.
yeah.
And we can also suggest
Right?
that the student added a catalyst.
Right. So you're probably thinking along the case that if it were an endothermic reaction, or sorry, exothermic reaction, right, and it was reversible, right? If it were an exothermic reaction and it was reversible, and you lower the temperature, so that would favor the exothermic side, and so more product will be formed. Is that what you're thinking, Sobia?
Yes.
Right, but that's not the case over here because it's not reversible, right? So those
Yeah.
so those equilibrium things are only for reversible reactions, mostly, right? I mean, they are applicable for one-way forward reactions as well. You can tweak them to get the best result, but equilibrium, the whole concept of equilibrium applies to reversible reactions. Okay, so that's not what we have here, and so that concept will not be applied for this particular scenario. Haram,
Okay.
you were saying something?
Yeah.
Yeah.
That we can also suggest that the student added a catalyst.
Again, the catalyst would cause it to happen more quickly. You can't see it happening more
Yes.
quickly. What you're seeing is more product being formed. More product being formed means you have more reactant, right? It's like you're making a dish, right? You take one egg and fry it as a right. You get one fried egg, obviously. You take or you make an omelette out of one egg. You get a certain size of omelette. You make an omelette out of three eggs. You get a bigger omelette,
Yeah.
right? Same thing, right? Now, sketch the curve expected in experiment 1 if experiment 1 is repeated using magnesium powder instead of magnesium ribbon. All other conditions remain the same. Now, this is where the rate will be affected. What do you think is going to happen?
Can you show the question again?
Question, see if we can tweak this. There you go. Right? C part 3.
Haram, you can take over.
Do you understand the question?
No.
Okay. Now, what affects the rate of reaction? Right? As I said, that equilibrium concept applies for reversible reactions, but the things that affect rate of reaction, right? For is magnesium ribbon a solid or a liquid or a gas?
Gas.
Magnesium ribbon is gas.
No, wait. You're talking about your magnesium ribbon. It is. It is solid.
Yes, right. So what change to a solid reactant affects the rate of reaction?
The increase in the collision.
No, you're going to say something before that. You were going to say something instead of collision. What was that?
Frequency of collision.
No,
Oh,
Haram.
wait.
Yeah.
What affects the rate of reaction of solids?
Can you repeat that again?
What affects the rate of reaction when you have a solid reactant?
Um, Maybe a gas?
Gas?
No, not a gas.
Okay, what's happening
Temperature?
over here? You had magnesium ribbon, right? You can see
Yeah.
that coiled thing over here. Now they're using magnesium powder.
Powder has a higher surface area than.
Good, right?
Okay, I was hesitating on that. I
I
thought.
know that's why I was pushing you. I know you were hesitating on that,
Yeah. Okay.
right? So the more the surface area for a solid, right, the more the rate of reaction.
Yeah.
And the rate of reaction means that the reaction is not going to produce more product, it's going to happen quicker. So you're going to get the same but in lesser time. So now experiment 1, what is the graph going to look like?
Mm. It's gonna be steeper than experiment one.
Yes, and
Uh, the curve should level off earlier.
yes, good. All right, so you're starting from here. Again, excuse that the curve is not going to be proper. But all right, you're going to start from here and you're going to have a steeper. All right, so in the exam, you need to practice, and for this, you need physical papers. Oops. So it should be like that. Now keep in mind, in your exam, the curve should be very smooth, not like mine wobbling all over the place.
Like the line should be,
Smooth.
it shouldn't be wobbly.
No.
Well, I'm not good at drawing. That's not a lot.
And that's why I brought it up. You need to practice. You need to practice having to draw physically on paper with pencil.
Okay.
Okay, so arrange for that just these graphs where you need to draw on the graph or make a graph, right? Not all the past papers. Although I would suggest that you have a notebook with you
Yeah.
and you write your answers. You don't need the whole printed paper. Okay, you write
Yeah.
your answers in your notebook physically, right? Pen on paper, because again your exam will be physically written on paper. It's not an
Yeah.
e-exam, right? So if you're not in the habit of writing it out, then you will have problems in actually attempting it when you are giving the actual paper,
Mm.
right? So I've told you, and so you should be right.
Aware.
Yes, right. You should not have an excuse, and even if you do, it's not going to work because right, this exam counts,
Mm.
right? It's your board exam. So
Yeah.
yes, be in the practice of writing on paper, your writing speed, timing yourself to complete it within the time period, and making these graphs with proper smooth lines, right? And your line should not be like super thick, like oh, super thick line, no, right? It should be okay. Fine, we adjust the thickness in this guy, uh, right? It should be. Come on, give me nice. Can I go below one? Right, so it should be a fine line and it should be smooth like that, something like that. Okay, so
Wow, that was smooth.
I know, look at that. Obviously not what I want to draw, but you get the point.
You can draw smoothly if you want to.
I know I was pretty good once upon a time.
Once in a blue moon.
No, once upon a time, not once in a blue moon. They're two very different things. You do know I know English.
Yeah.
Okay, so we're done with this question. Next. So there's a lot of text over here. A student investigates the. Do we have time? We do have time. A student investigates the reaction between dilute hydrochloric acid and two different aqueous solutions of sodium hydroxide, labeled solution A and solution B. Alright, so they're probably going to have different concentrations, but we have hydrochloric acid and sodium hydroxide, right? And that's going to give us sodium chloride. I didn't ask you because I assume you know this, right?
Mm.
So this is all aqueous and the water is liquid. Oh, by the way, right? We didn't balance. So when you're writing out equations, you need them to be balanced. So with magnesium and 2HCl. Right, and so you got MgCl2 and H2 there. So that's balanced. Okay.
Okay.
So the student does two experiments. The student rinses the burette with dilute hydrochloric acid, okay, fills the burette with dilute hydrochloric acid, all right, runs out some of the acid so the level of the acid uh, is on the burette scale, so that basically means it's at 0. Using a measuring cylinder to pour 25 centimeter cube of solution A into a conical flask, adds 5 drops of thymophthalene indicator to the conical flask. Swirls the flask while adding the acid from the burette to the conical flask until the solution just changes color. Okay. Then the student empties and rinses the conical flask with distilled water. Repeats experiment 1 using solution B instead of solution A. Okay. So figure 2.1 and 2.2 use these to record readings for experiments 1 and 2 in table 2.1 and complete table 2.2. Okay. So what's the table now? You've got final burette reading, initial burette reading, and volume of dilute hydrochloric acid added. Okay, so experiment 1, what's the final reading over here? So this is the final reading.
Okay.
Just a sec, sorry. Yeah, so this over here on the right is the final reading. What is the reading you can get out of this?
29.5.
29.5, right? So the reading is increasing, going down.
Yeah.
The reading is increasing, going down. Right, so 29, 29.1, 2, 3, 4, and 5. And you're looking at the lower meniscus. Don't be confused by the slight curve at the edge that's coming at 29.4. You need to read the meniscus. That's 29.5. Do you agree, Sobia? Right, so you have the final reading for experiment 1 is 29.5. Right, by the way, this is how you construct the table. Right, whatever things you're noting, you write that and the unit in which you're noting them. So this is centimeter cubes. You have the labels of which, like what you're noting them for. So that's 29.5 for experiment 1. What is it for experiment 2, the final reading?
29.1.
29. Apparently Sobia wants a turn. So Sobia, you can tell me the initial readings.
No, I don't want to turn. I'm confused.
Okay, what are you confused about?
I can let Haram take the spotlight out of hand, but how is it? Okay, for experiment 1, I cannot tell if the initial reading and final reading is increasing or decreasing.
It's increasing, right? First of all, see the trend of the numbers. Which one's bigger, 3 or 5?
5.
Obviously.
Yeah.
Right? And so you see the numbering. The numbering is increasing while going down.
Yeah.
Right? So this
Yeah.
is the burette. Right? It has like a nozzle tap or something. Right? And so these are the numbering. So you start off from 0 over here, and then you 1, 2, and all of that, all the way down till 50. Right? Normally. And so when you're going down, the value, like the reading,
Yeah.
is increasing. Right? Now,
Yeah.
obviously, right, the volume is getting lesser. Right? Because when you open a tap, it's flowing out. Right? But the
Yeah.
reading is increasing, meaning that you started off over here. What's the reading over here, Sobi?
Where?
The initial reading in figure
Uh,
2.1.
it's 5.
How is it 5?
Wait. It's reaching like 4.1.
4.1, right? So It started off at 4.1 and then it went to 29.5, right? So what you've done is you've used that much volume. We're going to calculate that you've used that much volume, right? And so the reading is increasing because you started from here where, right, you hadn't used anything, or right, it was empty till this point, and then you used it and you went up to 29.5. So you use that much volume, which is going to be the difference. Okay, what's the initial reading in experiment 2?
It is 16.4.
Yes, good. Right, so you've got 4.1 and 16.4. Now how do you get the volume? You subtract.
Yeah,
Right,
that's true. Yeah,
so tell me what the answer should be. Did that clear out your confusion?
yeah, yeah. You do.
Okay.
Why did we use the negative sign for the initial
Oh,
reading?
it's not a negative sign. I just put minus because you're going to subtract.
So it will be
You're going to subtract the initial reading from the final reading.
so it's gonna be 29.5 minus 4.1.
Yes.
Okay.
Right. This is for subtraction. It's not a negative sign.
We
Right.
will
In
like
in
subtract.
in in your table, you will not put this.
Yeah. Okay.
You will not put the minus sign.
We will subtract 4.1 from 29.5 minutes.
Yes. Yes.
That
Right.
would give 25.4.
Right. And so that's giving you 25.4. And so what you're finding is the volume used. How is it the volume used? Because you started at 4.1 and you ended at 29. So whatever volume is between this range is what's the that's the volume you used.
Correction, it is 25.4, not 24.5. Yeah.
And do we have to write the units as well?
The units are given over here. That's what I mentioned, right? Because they're already given in the heading, you don't need to write them again.
Okay.
Right? So when I'm reading 25.4, it's given it's in centimeter cube. So I know that any value over here is in centimeter cube. What about the next one, Sobia, for experiment 2?
Uh, 12.7.
So you can see that those are very, very different results.
Yeah.
Okay. Now this is experiment 1 is for solution A, and this is for solution B, right? Okay. Now, first of all, what is the color change that is observed? So basically they're asking, right, they added thymophthalene to the conical flask which had the sodium hydroxide, right? So the color change will be from alkaline to acidic. So what's the color change of thymophthalene?
Pink.
No,
From yellow to orange or
that that that's
orange.
that's methyl red. Sorry, methyl orange.
Red.
No. In alkaline, it's blue,
Two colorless.
the colorless. Right? Again, you need to check which indicator is being used. So this is thymophthalene. Okay? So blue to
Yeah.
colorless. Now, state which solution of sodium hydroxide is more concentrated.
Solution A is more concentrated
Why?
We
because it will be used to neutralize the solution or to neutralize the acid.
Neutralization is happening in both cases. Why are you saying that solution A is more concentrated? What does concentrated mean?
Yeah.
What does concentrated mean?
More thick.
More?
Not thick.
Um, the we compared the volumes.
Yeah. So which one is requiring more acid?
Yeah, so it's experiment one.
Experiment one, right? And experiment one is solution A. So solution is more concentrated because it requires more hydrochloric acid to be neutralized,
So it took exactly like twice as much acid.
right?
If I'm not
Solution A because it requires more volume of HCl for neutralization. Right? I'm just asking what does concentration mean in terms of sodium hydroxide?
in terms of hydroxide.
Yeah.
Uh, okay, so wait. It means like the amount of hydroxide ions present in the specific volume,
Good. So more hydroxide ions per unit volume.
which is moles, right?
Let's not go into the technical details. It's just
Oh,
more ions per unit volume.
yeah.
Okay. Now deduce the simplest whole number ratio of concentration of solution A to concentration of solution B, right? So the ratio is 25.4 over 12.7, right? So what is that going to give you?
2.
2, right? So that means solution A is twice as concentrated as solution B.
Yeah.
And so the ratio is 2 is to 1.
Hmm.
Okay. State the volume of hydrochloric acid needed if experiment 1 is repeated using 10 centimeter cube of solution.
We will multiply 25.4 by 10 and divide it by 24.
So what did you use initially? You used 25 centimeter cube.
Yeah.
Right. So what are you doing over here?
Volume of acid,
Yeah. So how much?
10 centimeter cube divided by 25 centimeter cube, multiplied by 25.4,
10 divided by
25,
25 into,
uh,
5.
25.4. By the way, are you writing, sir?
no,
Oh, so you're 5.3. It would give us,
That will give us 10.16.
yeah, yeah.
okay. So what's the concept behind your calculation?
Mm, So we need to find the like the volume of hydrochloric acid needed for like 10 centimeter. We use the results from experiment one. Am I right?
Yeah, yeah, yeah.
So that's how I did it. I mean, I don't know how to explain more.
Okay, so basically, right, you needed 25.4 centimeter cube HCl for 25 centimeter cube of NaOH. Right, so what you do is, okay, fine, how much is 1 centimeter cube NaOH? And so for that, you do 25.4 divided by 25. That's HCl and that's NaOH. right? And then you
Yeah.
multiply it by 10. So that's for 10 centimeters, and you get this answer.
Yeah. Are we done for the day?
This question carries on. So yeah,
Yeah, we can do the both E part as our last question.
uh, no, I'll stop here because E and then F carried on is sort of continuing that.
You're saying it's connected?
It does seem to be that way.
Okay.
Even if it's not, I'll stop. So we'll continue this the next time, inshallah.
Inshallah. Okay.
All right,
Okay.
good job today.
As usual.
Ah, don't get a fat head.
I mean, I'm proud of myself.
Well, you can pat yourself on the back.
Yeah.
Okay. All right.
Yeah.
So see you guys next time, inshallah.
Okay then. Allah Hafiz.
Allah.